Hi, Stu Schwartz from MasterMathMentor.com. This is video BC20. The topic is Comparison of Series, and it covers the BC Manual, pages 103 through 105. In order to use the convergence test we have studied so far, the terms had to be fairly simple and had to be in an exact form. Any deviation, however slight, means that the convergence test could no longer be used, and it could make a difference in whether the series converges or diverges. For instance, summation n equals 1 to infinity of n over the square root of n squared plus 1 fails the nth term test, but summation n equals 1 to infinity of n over the square root of n cubed plus 1 does not. Summation n equals 1 to infinity of 1 over n squared is a p-series, but summation n equals 1 to infinity of 1 over n squared plus n is not. Summation n equals 0 to infinity of 1 over 4 to the n power is a geometric series, but summation n equals 0 to infinity of 1 over 4 to the n plus 1 is not. And summation n equals 0 to infinity of n e to the negative n squared has an expression that can be integrated, while summation n equals 0 to infinity of e to the negative n squared cannot. In this video, we will examine two comparison tests that allow us to compare an unknown series with complicated terms to series with far simpler terms whose convergence or divergence has already been established. The series we will usually compare to are the divergent harmonic series, summation n equals 1 to infinity of 1 over n, the convergent p-series, summation n equals 1 to infinity of 1 over n squared, the divergent p-series, summation n equals 1 to infinity of 1 over the square root of n, and the convergent geometric series, summation n equals 0 to infinity of ar to the nth power if r is less than 1. You should memorize these four series as they come up all the time. The first test is called the direct comparison test. I will explain it first using the symbols of the test itself, and then I'll explain it in English. The direct comparison test starts off with the idea that we have 0 is less than a sub n is less than b sub n for all n greater than capital N. What this means is that we have two series, an A series and a B series, and we're going to look at term by term. And we find that the terms are all positive, and the A series term is always less than the B series term, starting at some value of n. If that is true, then if summation n equals 1 to infinity of b sub n converges, then summation n equals 1 to infinity of a sub n converges. Or if summation n equals 1 to infinity of a sub n diverges, then summation n equals 1 to infinity of b sub n will also diverge. So what this says is, if the larger series converges, then the smaller series must also converge. And if the smaller series diverges, then the larger series must diverge as well. Let us first try to determine the convergence or divergence of summation n equals 0 to infinity of 1 over 3 plus 2 to the n. This expression passes the nth term test as the limit as n approaches infinity of 1 over 3 plus 2 to the n is equal to 0, so it could converge. But it isn't geometric, It isn't a p-series, and the expression cannot easily be integrated. A comparison test at this moment is all that is left. But what do we compare it to? We realize that 1 over 3 plus 2 to the n is similar to 1 over 2 to the n, and that series is a geometric and convergent series. 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus dot dot dot. If we look at the expression summation n equals 0 to infinity of 1 over 2 to the n plus 3, we get 1 over 4 plus 1 over 5 plus 1 over 7 plus 1 over 11 plus dot dot dot. And we realize that every term in this series is smaller than the term directly above it. So our conclusion is that since 1 over 2 to the n plus 3 is less than 1 over 2 to the n for all values of n, then because summation n equals 0 to infinity of 1 over 2 to the n converges, then summation n equals 0 to infinity of 1 over 2 to the n plus 3 also converges. Number 2, as we will see, is a little bit more difficult. We want to determine the convergence or divergence of summation n equals 1 to infinity of 1 over 4 plus the square root of n. Again, this passes the nth term test as the limit as n approaches 0 of 1 over 4 plus the square root of n is 0, so it could converge. It isn't geometric, and it isn't a p-series, and it is not that easy to integrate. So a comparison test at this moment is all that is left. But what do we compare it to? Our first thought is that this looks like summation n equals 1 to infinity of 1 over the square root of n, which is a divergent p-series. So our thought is that this too will be divergent. So we set up the first few terms of summation n equals 1 to infinity of 1 over the square root of n, and the summation n equals 1 to infinity of 1 over 4 plus the square root of n. And we see that in all cases, 1 over the square root of n will be greater than 1 over 4 plus the square root of n. So summation equals 1 to infinity of 1 over the square root of n diverges, and summation n equals 1 to infinity of 1 over 4 plus the square root of n has smaller terms. That means it could converge, which means that this test is inconclusive. We need to find another series to compare it to. Since we still believe that our series is divergent, we will compare it to another divergent series, the harmonic series, summation n equals 1 to infinity of 1 over n. And when we do that, we see that at first, again, the first few terms in 1 over n are larger than the first few terms of 1 over 4 plus the square root of n. But does that pattern continue forever? While we could do an analytic investigation, we will do a graphic one as it is easier to see. We will graph the denominators. Y equals x in blue, y equals 4 plus the square root of x in red. And while the red curve is above the blue curve for a little while, we see that when x is above 7, the blue curve will be always greater than the red curve. So, since n is greater than the expression 4 plus the square root of n, if n is greater than 7, it follows that 1 over n must be less than 1 over 4 plus the square root of n if n is greater than 7. So eventually, 1 over 4 plus the square root of n is the bigger series. So since 1 over 4 plus n is greater than 1 over n, and summation n equals 1 to infinity of 1 over n diverges, then summation n equals 1 to infinity of 1 over 4 plus the square root of n must diverge as well. The direct comparison test is difficult to use. You have to have a sixth sense whether your series is convergent or divergent, which helps you to choose your comparison series. And as we saw in number 2, the comparison series may give an inconclusive result. And even if the result is conclusive, you need to show that the two series behave in a certain way only after some unknown n number of terms. It is for these reasons that the direct comparison test is my last go-to test when trying to determine convergence or divergence. There are far better ones. There is a far better comparison test called the limit comparison test. It states if a sub n is greater than 0 and b sub n is greater than 0, and the limit as n approaches infinity of a sub n over b sub n is equal to L, where L is a positive number and finite, then the two series, summation of a sub n and summation of b sub n, either both converge or diverge. In English, this is what the limit comparison test says. You have a series a sub n that you'd like to determine whether it converges or not, and it has all positive terms. You then have another series, which we'll call a benchmark series, called b sub n, also consisting of positive terms. That you know whether this benchmark series will converge or not. You then look at the limit as n approaches infinity of a sub n over b sub n. And if you end up getting a positive number that is not infinite, then the two series a sub n and b sub n either both converge or both diverge. So if b sub n converges, then your series a sub n will converge as well. If the benchmark series b sub n diverges, then your series a sub n will diverge as well. Our benchmark series are the same as our comparison series were for the direct comparison test. We like to use the divergent harmonic series, summation n equals 1 to infinity of 1 over n. The convergent p-series, summation n equals 1 to infinity of 1 over n squared. The divergent p-series, summation n equals 1 to infinity of 1 over the square root of n. And the convergent geometric series, summation n equals 0 to infinity of a r to the n, where r is less than 1. Let us now look at the two problems we previously did with the direct comparison test and show how the results are much easier with the limit comparison test. For number 3, summation n equals 0 to infinity of 1 over 3 plus 2 to the n. We will compare this as we did with the direct comparison test to the convergent summation n equals 0 to infinity of 1 over 2 to the n. This is a geometric series. We look at the limit as n approaches infinity of 1 over 3 plus 2 to the n over 1 over 2 to the n. And we end up getting the limit as n approaches infinity of 2 to the n over 3 plus 2 to the n. This is equal to infinity over infinity, but using L'Hopital's rule for both numerator and denominator, we get 2 to the n natural log of 2 over 2 to the n natural log of 2. Limit as n approaches infinity is equal to 1. Therefore, as the limit is finite and positive, then summation n equals 0 to infinity of 1 over 3 plus 2 to the n does what summation n equals 0 to infinity of 1 over 2 to the n did, which was converge. 4 reads summation n equals 1 to infinity of 1 over 4 plus the square root of n. When we did this by the direct comparison test, we compared it to 1 over the square root of n and got an inconclusive result. However, for the direct comparison test, we will again compare it to the divergent n equals 1 to infinity summation 1 over the square root of n. Looking at the limit as n approaches infinity of 1 over 4 plus the square root of n over 1 over the square root of n, we get the limit as n approaches infinity of the square root of n over 4 plus the square root of n. This is infinity over infinity, but by using L'Hopital's rule, we get limit as n approaches infinity of 1 over 2 square root of n over 1 over 2 square root of n, which is equal to 1. Again, as this limit is finite and positive, then summation n equals 1 to infinity of 1 over 4 plus the square root of n does what summation n equals 1 to infinity of 1 over the square root of n did, which was diverge. Note that when we do the direct comparison, it does not matter which is in the numerator and which is in the denominator. Number 5 reads summation n equals 1 to infinity of 1 over an plus b, where both a and b are greater than 0. This is a form of the harmonic series, and we would like to show whether it is convergent or divergent. First, trying to do it by the direct comparison test, failing, and then showing that the limit comparison test is easy and conclusive. In doing the direct comparison test, we will first write our series, summation n equals 1 to infinity of 1 over an plus b, as 1 over a plus b plus 1 over 2a plus b plus 1 over 3a plus b plus 1 over 4a plus b plus dot dot dot. Our benchmark series will be summation n equals 1 to infinity of 1 over n, which is 1 plus a half plus a third plus a fourth plus dot dot dot. And of course, this is divergent. When we do the direct comparison, we are unsure if each term of summation n equals 1 to infinity of 1 over an plus b is smaller than the summation n equals 1 over to infinity of 1 over n. It all depends upon the value of a, so no conclusion is possible. But now we use the limit comparison test, and our benchmark series will still be 1 over n. So we look at the limit as n approaches infinity of 1 over n over 1 over an plus b. And we get the limit as n approaches infinity of an plus b over n, which is equal to a. As stated before, it does not matter which expression is in the numerator and which is in the denominator. If we had reversed them, then our limit would be 1 over a. But since a, or 1 over a, is positive, then summation n equals 1 to infinity of 1 over an plus b does exactly what summation n equals 1 to infinity of 1 over n does, and therefore our result is divergent. In problems 6 through 9, you are given 4 series and you are asked to find the possible convergence or divergence of each using the limit comparison test. 6 reads summation n equals 1 to infinity, 1 over 3n to the third minus 5n plus 7. We would like our benchmark series to be one that when we flip it, we will get cancellation with the highest power term. So we will use 1 over n to the third, which is a convergent p-series. So looking at limit n approaches infinity of 1 over 3n to the third minus 5n plus 7 over 1 over n to the third gives limit n approaches infinity of n to the third over 3n to the third minus 5n plus 7, and that is equal to 1/3. And since 1 over n cubed converges, then the series that we are given is also convergent. Number 7 reads, the summation n equals 1 to infinity of 1 over the square root of 4n minus 2. Our benchmark series will be 1 over the square root of n, which is a divergent p-series. So we look at limit n approaches infinity of 1 over the square root of 4n minus 2 over 1 over the square root of n, which is the limit as n approaches infinity of the square root of n over the square root of 4n minus 2, which is equal to 1/2. And since 1 over the square root of n is divergent, then our series in question is also divergent. Number 8 reads summation n equals 1 to infinity of n squared minus 5 over n cubed minus n squared minus n plus 2. For all its complexity, this is really an n squared over n cubed equal 1 over n problem. So we will compare this to the divergent 1 over n harmonic series. So we look at the limit as n approaches infinity of n squared minus 5 over n cubed minus n squared minus n plus 2, all over 1 over n. And this gives the limit as n approaches infinity of n times n squared minus 5 over n cubed minus n squared minus n plus 2. And that is equal to 1. So since 1 over n is divergent, then number 8 is also divergent. Number 9 reads summation n equals 0 to infinity of n times 2 to the n over 4n cubed plus 3. This illustrates one of the issues with the limit comparison test. What do we use as our benchmark? Our benchmark needs to be an expression so that when we flip it, all the terms cancel other than the numbers. So we will use a 2 to the n over n squared. And this is divergent, as the numerator is more powerful than the denominator, and it will fail the nth term test. So we look at the limit as n approaches infinity of n 2 to the n over 4n cubed plus 3, all over 2 to the n over n squared. This becomes the limit as n approaches infinity of n 2 to the n over 4n cubed plus 3 times n squared over 2 to the n. And the 2 to the n's cancel, and the n cubes cancel, and we are simply left with 1/4. So since 2 to the n over n squared is divergent, this series is divergent as well. We will see in a future test where we don't have to ask this question of what our benchmark is, and we can find a direct way to determine convergence or divergence of a series that is this complex. So far, we have looked at tests to determine the convergence of series with positive terms. But what happens if they have negative terms? And the series alternates in sign. We will examine this in our next video using the concept of alternating series.